Welcome back. In today's video, we are going to be talking about a special kind of sum called a Riemann sum. A Riemann sum. Don't be walking out of this house saying Riemann sum, please. German name, Riemann sum. Riemann. Hi folks, Editing Sam here, who did not necessarily like her original exposition of this topic. So I've rearranged a little bit of the material. So here are the new objectives for today. Today we're going to focus on what a Riemann sum is, how it is represented symbolically, the terminology associated with Riemann sums. We're going to get a little bit of practice calculating them, although the truth is that in previous episodes we already have had practice calculating them. What is a Riemann sum? If someone is talking about a Riemann sum for a function, specifically on an interval, say let's generically call it the interval from A to B, they're talking about a sum given by a somewhat specific type of formula. That sum needs to be of a formula that looks like this one. In summation notation, sigma, initial index 1, final index generically called capital N, f of x sub I star times delta x. Let's talk a little bit about what each of these quantities in this Riemann sum, what each of these quantities in this summation notation are standing for. Now this capital N here in the summation notation for a Riemann sum refers to the number of chunks, the number of pieces into which this interval has been split. So this capital N on the top of the sigma is communicating, take your interval from A to B and split it into n portions. What is this quantity delta x standing for? This quantity delta x is what's standing for the width or the length of each of these chunks or pieces into which your interval has been divided. So the length of each interval is this delta x. And this quantity inside the function, x with a subscript of I with a little star on top of it, this is just a random x value that you choose from within the chunk or the piece of the interval that is chunk number I. Now that's all very abstract and that's probably really complicated, but the truth is that in episodes 1 and 2, we've actually seen quite a large number of Riemann sums already. So let's compare this alphabet soup with the Riemann sums that we already encountered as we moved through the physical examples, the real-world examples in episodes 1 and 2. For example, let's go back to episode 1 and recall this scenario involving this car that was driving at a non-constant speed, and it was driving for 2 hours. In other words, it was driving over the interval of time from 0 to 2. Let me record that as a note on the side. The time interval in this example was 0 to 2. So in this case, the time interval from 0 to 2 is what is standing in the place of this generic interval in the Riemann sum, a generic interval here just from A to B. In this episode, in this example, it was specifically the interval of time from 0 to 2. Now in this particular case, the function that we were dealing with gave us a relationship between the time that had passed and the speed of this moving object. So in this particular case, the function that is in question is the function that tells me the relationship between time and speed. And in this particular example, that function is being communicated using a table. This specific function relating time and speed in this scenario is analogous to this generic function, generically called f of x, in this formula. Here it's the generic function f of x in this scenario, It was the specific function here relating the time that had passed with the speed of the car. Now, in this example, the number of pieces, the number of chunks into which this time interval had been divided was 4. There's this first period of time between 0 and zero point 0.5 units. There was this second period of time between half an hour and 1 hour. There was this third period of time between 1 hour and 1.5 hours. And then there was this fourth period of time between 90 minutes and 2 hours. So if I were to compare, once again, this specific example with what's showing up in this abstract formula, in this specific case, capital N, the number of sort of subintervals, the number of chunks, the number of pieces of this interval would be 4. There are 4 time intervals into which this big time interval has been split. So comparing this example with the one before, we have a split of 4 subintervals here. And how wide are each of these little pieces? How much time has passed between each of these little checkpoints? If I were to compare what I have here with what I have in this generic formula, the width of each little interval, the width of each little chunk, in this case would be delta x equals 0.5 because it's a half hour that has passed between each of these little checkpoints and each of these little intervals. Now, as we tried to estimate the distance traveled by the car during this time interval, given this information, we basically went into the table and we pretended that the car's speed remained constant over these sort of sub-intervals here. For example, we pretended that for the entire time between 0 and 0.5, the car's speed remained constant at 5 miles per hour. So what we did was on our first sub-interval, this first sort of window of time, this first half-hour period, we decided to choose at random the input on the right side of the interval. And by choosing that value at random, we have chosen the value of what we would call in this notation x sub 1 star. X sub 1 star is an x value chosen more or less at random from your ith chunk. So x sub 1 star would be a value chosen at random from this first period of time. And in this example, we chose the x value on the right-hand side. So xi star was 0.5, and the corresponding output at that value we decided was 5. Now, what did we do with that? We pretended that the car's speed was constant at this output of 5 miles per hour. And then we took that speed, we took that 5, and we multiplied it by the amount of time that we assumed the object had traveled at that speed. We multiplied it by 0.5. So here we see an example of f of x1 star, this random output value associated with this first interval, multiplied by the length, the width of that interval, delta x. That's the product that's going on here when we use the dirt equation, d equals rate times time, to get this first little bit of distance traveled, which was 2.5 miles, our estimate for that first time interval. And then we did the same thing for each of these other time intervals. Down here in yellow, we went ahead to our second time interval, where I is equal to 2. In this second period of time, we chose to assume that the speed was constant at 28. We basically made a random decision about what speed we were going to choose on that second interval. The amount of time, the delta x, was still half an hour. And so once again, we see this product of 28, the rate, the speed, times the length of time. So once again, we see this product f of x2 star times delta x. And we did it again for the third subinterval. We did it again down here in green, where we have what we call, in our current notation, the third period of time. We basically chose a speed that seems at least kind of plausible, and then we multiplied it by the amount of time. And then again here at the bottom, the fourth subinterval, we basically just decided we chose a speed that seemed not too insane, and then we multiplied that by the amount of time. And then here at the bottom, we see the sum. We see the sum where we added together all these little bits of distances together. All these little expressions got added together in a sum to find the total distance. So this would be an example of a Riemann sum that we have already done. We have already calculated, in this case, to estimate the total distance traveled by the car. This is an example of a Riemann sum calculation. We've done many, many more Riemann sum calculations. In this example, in this Riemann sum, the interval that we are dealing with is the interval of positions corresponding to the length of the rod. In this example, the interval in question would be all the way from 0, the left end of the rod, to 10, the right end of the rod. And we've split that rod into 1, 2, 3, 4, 5 chunks. So n would be 5 in the notation of the Riemann sum. And how wide are each of these chunks? Each of these chunks is 2 units wide. So 2 units wide, 2 would be the value of delta x in this example as compared to the generic Riemann sum formula. In this particular case, our function f of x is described using a table, and that function relates position and density. And we didn't finish this example for, to save time, but here once again you see this pattern of you sort of choose a random value between the two ends of your chunk, and you get that sort of random output value. Here we might have assumed maybe 3.5, some random output value between 2 and 5. And we multiplied that random output value by the length of the chunk to estimate the mass of that chunk. So this would, for example, be in this problem, the output that we chose for the first chunk times the length of the first chunk, and this would give us the mass of the first chunk, and then I would have to add all of these together, sum them up to find the total mass of the rod. Cutting over as well to episode 2, when we saw this example involving the crystal. In this particular case, our interval would be from 0 to 6. That would be the interval of the positions. And in this case, the number of chunks is 1, 2, 3, 4, 5, 6, 6 chunks, and the width of each chunk would be delta x equals 1 unit. And so in this particular case, we chose to think of our xi star as being the left-hand value. And then the associated output that we chose was the one on the left. And here you can see once again this product showing up of this value that we chose, fx1 star, times the length of the chunk, area times width, giving me volume in this particular case. And then the sum, here we are, the sum of all of those products gave me the total estimated volume of the crystal. So these 3 examples, all of these are Riemann sums used in different ways with different functions to estimate things like distance traveled, mass, and in this case, volume. Here we're just taking this idea that has shown up in each of these examples and sort of abstracting it, making it general, noticing the patterns that have shown up in those three scenarios, and taking that pattern and turning it into an abstract formula. Sum from your first chunk to your final chunk, f evaluated at some random x value inside of the chunk, multiplied by the width of the chunk, add those all together, and that total is what we call a Riemann sum, used to calculate things like distance traveled, like mass, and like volume. So as we noted, as these exercises are related to integrals, you can imagine that Riemann sums are going to be very, very closely related to integrals. As these sums became integrals, as the number of data points gets larger, as these sums became integrals, as the space between the data gets smaller, these Riemann sums will become integrals as the space between these data points gets smaller. More on that in the next couple of episodes. Now let's get some practice calculating an abstract Riemann sum using this formula. So for example, someone says calculate a Riemann sum for this function f of x equals 2 minus x on the interval from 0 to 1 using n pieces, using n chunks. Now, as we have seen in episodes 1 and 2, if you are not given a table of data for your scenario, if you are given a function instead of a table of data, our typical process is to create the table ourselves using the formula that has been provided to us. So I'm going to start by creating a table. So here, for example, in the table, I'm going to put down some x's. And here, for example, in the table, I'm going to put down the corresponding f of x values, creating my own table. Now, the interval that I'm given to work with is from 0 to 1. So my first x value is going to be the first value in that interval is going to be 0. And now I need to split this interval into 5 pieces. Now, thought exercise. If I split this interval from 0 to 1 into 5 pieces, how wide will those pieces be? How far apart will my data points be? Well, if I want to take an interval of length 1 unit, from 0 to 1 unit, and I want to split that interval into 5 pieces of equal size, then I can take the length of that interval, divide it into 5 portions to find out that my data points need to be 0.2 units apart. So in the language of the Riemann sum, delta x would be 0.2 to get 5 chunks out of this interval. So if my data points are 0.2 units apart, then from 0 to the next data point would be 0.2. From 0.2 to the next data point would be 0.4. From 0 to the next data point would be 0.6, and then 0.8. And so now I have set up my 1, 2, 3, 4, 5 pieces, 5 chunks for this interval. Now let's use the function here to calculate the associated y values. 2 minus 0 would be 2, 2 minus 0.2 would be 0.8, 2 minus 0.4 would be 0.6, then 0.4, then 0.2, then 1. These would be the y values associated with these x values in our Riemann sum. Now I have a decision to make. If I go in, for example, to the very first chunk of this interval, corresponding to an I equals 1, I need to make a decision about which x value in that interval I want to use. I have to make a decision. Now, the two most common choices are to either always take the left x value or to either take the right x value out of each chunk. You can also take values in the middle of the chunk, but it's not often worth the effort. It's typical to take either the left value or the right value. When you take the left x value every single time, um, that is what is sometimes called a left Riemann sum. And when you take the x value on the right side every single time, this is what's sometimes called a right Riemann sum. Perhaps for an example, I'll show you what it would look like to take a left Riemann sum and to choose the x value that's on the left-hand side of each of these intervals. If I made that decision, then the first x chosen out of the first chunk would be the f on the left side of the chunk, the x value of 0. And the output corresponding to that decision would be, according to the table, according to the function, 2 units. If I made the decision to take the left value on each chunk, then on chunk number 2, I would use this value on the left end, 0.2 units. I would decide that the x taken out of the second chunk would be 0.2, and then the y value associated with that would be 1.8. If I'm going with a left Riemann sum, then the left Riemann sum would say the third chunk, I'm going to use the left x value, which would be 0.4, and the associated height, the associated output would be 1.6. A left Riemann sum would have x4 star to be 0.6, and the associated output would be 1.4 according to the table, and then x5 star, the x taken out of the fifth chunk. If I went with a left Riemann sum, I would take the left x, the leftmost x out of the fifth chunk, and the leftmost x is given by 0.8. Giving me a corresponding output of 1.2. Now to finish the left Riemann sum, all I would have to do is take each of these output values and multiply them by the delta x. So I would have 2 times delta x. I would have 1.8 times delta x. I would have 1.6 times delta x. 1.4 times delta x, 1.2 times delta x. And the sum of these values, would be the value of the Riemann sum asked for in this problem if I decided to do a left Riemann sum and take the left x value on each interval. Now, of course, it is also possible to make other decisions about what x's from each chunk you're going to choose. For example, I could also answer the question using a right Riemann sum. And the difference between the left Riemann sum and the right Riemann sum is the specific value that you decide to take out of each chunk. If you go with a right Riemann sum, then the x value you're taking out of the first chunk is the x value on the right side. So in this situation, the x value out of the right side of this first chunk would be 0.2. So my first x value chosen out of the first chunk would be 0.2. And the corresponding value of my function would be 1.8. That would be the first value in a right Riemann sum. And then so on and so forth. If I decide to do a right Riemann sum, then the x value I choose out of the second chunk would be this x value on the right side of the chunk, which is zero point 0.4. If I make that decision, then my corresponding output on the second chunk would be 1.6, and so on. Let me quickly fill in the rest of these values. Now the value of my Riemann sum has changed a little bit. Now if I take all of these different outputs and multiply them by my delta x, and I add all of those results together in that sum to get that total, then the value has changed, no longer 1.6, but now, according to the calculator, my Riemann sum has a value of 1.4. So making different decisions about the x star that you choose out of each chunk does change the value of the final answer slightly. But remember that that is okay. Remember that in these physical applications that we are referring to when we construct this abstract Riemann sum formula, in these physical applications, everything that we're doing is just an estimate, right? Just an estimate. So different people taking different approaches will absolutely get different estimates, but that's okay because the idea is that both of these estimates are in the ballpark of the real answer. So maybe the real answer is somewhere between these two values. Maybe the real answer is something like 1.5. That seems plausible to me. So this is how we calculate a Riemann sum for a function. Just to briefly recap, what did we do? We said, okay, this is the interval you're interested in, and this is the number of sub-intervals that you're interested in. I'm going to set a table up. I'm going to write down the first x value in that interval, and then I'm going to break that interval down into 5 pieces of equal length. By splitting that interval into 5 pieces, I get my x values into this table. Then I plug those x values into this function, and I get the y values out of this table. Then I decide, if I'm not told, I decide what values of x star I'm going to pluck out of each interval. And based on that decision, I get the outputs corresponding to those x's. Finally, once I've gotten all those outputs, I take all of those outputs, multiply all of them by delta x, and add the results together. And that process is what gives me the value of this Riemann sum.